All right, now the next topic we looked at was systems of ODEs. Systems of ODEs. So basically, if you want to describe the problem, we had n unknown functions this time. So given n unknown functions, let's say x1 of t to xn of t with one independent variable t and also n equations. So we are given n unknown functions, one independent variable t, and n equations. The goal, n differential equations, or n ODEs. The goal was to find the unknown functions x1 of t to xn of t. So to solve a system of ODEs, first write in the matrix form. First we had to write in the matrix form. So let's say x prime equals ax. And here is, let's say x is our vector x1 of t to xn of t. And a is n by n. So basically we looked at a first order system of ODEs. A first order system of ODEs. And to solve this system, if you remember, first we had to find the eigenvalues, eigenvectors of A. First, find the eigenvalues and eigenvectors of A. And how did we find eigenvalues, eigenvectors? So if we solve for determinant A minus lambda I equals 0, then the roots will be eigenvalues. And once you find an eigenvalue, let's say if lambda 1 is an eigenvalue for A, if lambda 1 is an eigenvalue for A, then how do we find the eigenvector corresponding to this eigenvalue? Solve the system, basically AX equals lambda 1x, which is same as A minus lambda 1I times x equals 0. And any non-zero solution of this system will be an eigenvector for lambda 1, because eigenvector must be non-zero. And as long as lambda 1 is an eigenvalue for A, this system will have a non-zero solution. So any non-zero solution of this system will be an eigenvector for A. Now, how many linearly independent eigenvectors will A have? So if A has an eigenvalue, let's say lambda 1 with multiplicity let's say n1. So multiplicity means, you know, the power that appears in the characteristic polynomial for A, like when you expand determinant A minus lambda I equals 0, this will be a polynomial in lambda. So after you factorize that polynomial, let's say if you have lambda minus lambda 1 to power n1 appeared in your polynomial, then that means lambda 1 is a root or eigenvalue for A with multiplicity n1. So this power here that appears in the factorization of that polynomial is called multiplicity of the eigenvalue. Now, if A has an eigenvalue lambda 1 with multiplicity n1, then A has at most n1 linearly independent eigenvectors. At most n1 linearly independent eigenvectors and at least one. Whenever you have an eigenvalue, it will have at least one linearly independent eigenvector. But how many at most? At most is same as the multiplicity of that eigenvalue. So for example, if eigenvalue has multiplicity 1, which means if lambda 1 is a single root for your polynomial, then if multiplicity is 1, then that means at most one linearly independent eigenvector. Well, it's also at least one linearly independent eigenvector, which means it must have exactly one linearly independent eigenvector. So if multiplicity is 1, then you will have one linearly independent eigenvector. But if multiplicity, let's say, is 2, then you will have at least one and at most two linearly independent eigenvectors, which means either one or two linearly independent eigenvectors. So this is about the number of linearly independent eigenvectors. So you will find eigenvalues and eigenvectors for A. Now suppose that, let's say if let's say lambda 1 to let's say lambda 1 and lambda 2, let's say, are eigenvalues with eigenvectors. Let's say if you have two eigenvectors, let's say eta 1 or C1 and C2, then our two linearly independent solutions will be, let's say, x of t, then let me say C1 times e to power lambda 1t, and C2 e to power lambda 2t will be two linearly independent solutions, of x prime equals ax. So this is straightforward. If you have two different eigenvalues with two different eigenvectors, then we can form two linearly independent solutions this way. So C1 is a vector. E to power lambda 1t is not a vector, it's a function of t. So overall, this is a vector. This is also a function of t. The vector part is included here. The dependency on t is included on this part. So overall, this is a vector and it's a function of t. Now, this is in the case where we have two eigenvalues with two eigenvectors C1 and C2. It's a two real, if lambda 1, lambda 2 are real eigenvalues. Now, what about if we have a repeated eigenvalue? So let's say if lambda 1 equals lambda 2 equals lambda is a repeated eigenvalue, then we can have two possibilities, because we said that if it's a repeated eigenvalue means the multiplicity is 2. Repeated eigenvalue means you have, let's say, lambda minus lambda 1 squared appeared in your polynomial. So then the multiplicity will be 2. And we say if the multiplicity is 2, we can have at most 2 linearly independent eigenvectors. So that means either 1 or 2 linearly independent eigenvectors. Now this depends then if you have 2 linearly independent eigenvectors, so case 1, if let's say C1 and C2 are 2 linearly independent eigenvectors. Again, the recipe will be similar to what we described above. Then C1 e to power lambda 1t to C1 e to power lambda t and C2 e to power lambda t will be 2 linearly independent solutions. Dependent solutions of this ODE. And case 2, if let's say this eigenvalue has only one linearly independent eigenvector. So let's say if C1 is the only linearly independent eigenvector corresponding to lambda, then what will be the 2 linearly independent solutions? Then C1 e to power lambda t and C1 t e to power lambda t plus e to power lambda t times d are 2 linearly independent solutions, 2 linearly independent solutions of x prime equals ax. And what is d here? So I already explained what C1 is, what lambda is, what is d, and here d is the generalized eigenvector for A, which means like A minus lambda I times D equals C, or C1. And this can be also written as, because A minus lambda I times C1 is 0. C1 is eigenvector, so A minus lambda I times C1 is 0. So if I multiply both sides with A minus lambda I one more time, then I can say that A minus lambda I squared times D is 0. So that's why this is called a generalized eigenvector, because for eigenvector, I need A minus lambda I times C equals 0. So instead of A minus lambda I times C equals 0, I have here A minus lambda I, the whole squared, times D equals 0. So that's why this is called a generalized eigenvector for A. So once you have the generalized eigenvector D, then you can construct your two linearly independent solutions as C1 e to power lambda t and C1 t e to power lambda t plus e to power lambda t times D. So this is in the case of having a repeated eigenvalue, and case 3, if lambda 1 and lambda 2 are two complex valued eigenvalues corresponding to the eigenvectors C1 and C2, which will be C1 bar. So if I have two complex eigenvalues, if one of them is lambda 1, the other one, it can be shown that it will be lambda 1 bar, the complex conjugate of lambda 1. So here lambda 2 will be same as lambda 1 bar. So it can be shown that if lambda 1 contains some imaginary part, then complex conjugate of lambda 1 will be also an eigenvalue for A. So in the case of A that is 2 by 2, if I have two eigenvalues, which are lambda 1 and lambda 1 bar, then the eigenvectors will be C1 and C1 bar. So how can I construct the two linearly independent solutions in this case with corresponding to eigenvectors C1 and C1 bar? So we just need to focus on lambda 1 and C1. So construct or form, then construct C1 e to power lambda 1t. Now C1 has some real part, imaginary part. It's a vector. It has some real part, imaginary part. Lambda 1 also has some real part, imaginary part. So overall, this is a complex valued function. It will have some real part and some imaginary part. If you take the real part and imaginary part, you can call them y1 and y2, and those will be your two linearly independent solutions for your system. So then we can say y1 equals the real part of C1 e to power lambda 1t, and y2 equals imaginary part of C1 e to power lambda 1t will be two linearly independent solutions. I call them X, let me call them X1 and X2. X1 of t equals this, and X2 of t equals this, will be two linearly independent solutions of X prime equals AX. So in the case of having two complex valued eigenvalues, just focus on one of them. Forget about the second eigenvalue and second eigenvector. Just look at the first eigenvalue and first eigenvector. Construct this. This will be complex valued function. Take the real part and imaginary part as your two linearly independent solutions for this system. And in this chapter, we also looked at the non-homogeneous case. Non-homogeneous case, where we have, let's say, x prime equals ax plus g of t, and g of t is a vector. And we wrote x, the general solution. General solution again can be written as x equals xc plus xp, where xc, or the complementary part, is the solution of the homogeneous system x prime equals ax. xc is the general solution of x prime equals ax. And what about xp? xp is a particular solution. And how can we find the particular solution? Well, how did we find the particular solution in the case of, let's say, single ODE? Well, we could use undetermined coefficients or variation of parameters. And again, both these methods can be applied here as well. A particular solution which can be found using undetermined coefficients. Undetermined coefficients or variation of parameters. And again, the formula for variation of parameters is similar to before. So if you want to find, let's say, xp, xc, these are vectors. Now, if you want to find the vector xp, you can write it as capital X times integral capital X times capital X inverse times g of t dt. Now, this is a matrix. Is going to be, let's say, in the case of 2 by 2, it will be, let's say, 2 by 2 matrix, and this will be 2 by 1 vector. And overall, the answer will be 2 by 1 vector. And what is capital X? So here, capital X is the matrix whose columns are x1 of t and x2 of t. And these are the linearly independent solutions of x prime equals ax. We already explained how to find two linearly independent solutions of x prime equals ax. Remember, we had to find the eigenvalues, eigenvectors, and then depending on whether we have real or complex or repeated eigenvalues, we explained how to find two linearly independent solutions for x prime equals ax. So once you find those two solutions, call them x1 of t, x2 of t, put them as columns of this matrix capital X. So x1 of t, x2 of t will be used as columns of the matrix capital X. And then this matrix capital X will be invertible. Why will it be invertible? Because we know that if you have a matrix with linearly independent columns, then it will be invertible. A matrix with linearly independent columns is always invertible. You saw this in Math 252 linear algebra. So capital X is invertible. Once you find capital X inverse multiplied with g of t here is a vector, then this will be a vector. It will be a vector and also a function of t. Each component is a function of t. Integrate each component separately, and then you will have, again, a vector after you integrate each component. So this will be a vector, and if you multiply this matrix by this vector, again, you will get a vector. And that will be your particular solution. And then the general solution, as we explained earlier, can be written as xc plus xp. This one general solution of x prime equals ax, and this one a particular solution which can be found using this formula or using undetermined coefficients method. The next topic we looked at was Laplace transforms. And if you remember, we defined Laplace transform of a function, let's say f of t, as integral 0 to infinity e to power minus st f of t dt. And this becomes a function of s, because the integration is over t, so it becomes a function of s, denoted by capital F of s. And now there are a few questions here that could be asked. One is for which functions the Laplace transform exists. And we saw that Laplace transform f of t exists if f of t is a piecewise continuous function, and it is of exponential order. And what was the meaning of being of exponential order? The meaning was absolute value f of t is less than or equal to m times e to power ct for some constants m and c bigger than 0. If absolute value f of t is less than m e to power ct for some constants m and c, then we call the function an exponential, a function of exponential order. And if it's of exponential order and if it is piecewise continuous, then Laplace transform f of t exists. So this is one question that we answered. Another question, why is Laplace transform important? Because, well, we have a function of t. Because Laplace transform is a basically function whose inputs and outputs are functions themselves. So we feed Laplace transform a function and we get another function back. But then someone could ask, what's the point? We already had a function. Why do we need a new function? Original function is a function of t. The new function is a function of s. But what's the point? Well, the point was, the most important property was that the Laplace transform helped us to disappear, make all the derivatives disappear. So once all the derivatives are disappeared, then we won't have an ODE anymore. It's hard to solve an ODE because of the derivatives. But if all the derivatives are disappeared, then I will have simply an algebraic equation instead of a differential equation. I will simply have an algebraic equation. I can solve that algebraic equation to find capital F of s. And once I find capital F of s, then I can apply inverse Laplace transform to get the original function back, the function that I'm looking for it. So, after applying Laplace transform, all derivatives will be disappeared. Another important property of Laplace transform, it was basically Laplace transform is a linear operator. So what does that mean? That means Laplace transform, let's say f1 plus f2 is same as Laplace transform f1 plus Laplace transform F2, and also Laplace transform CF is equal to C times Laplace transform F. We also saw that Laplace transform is one-to-one and therefore invertible. Laplace transform is invertible, and inverse Laplace transform is also linear. We just said the meaning of a linear operator. And inverse Laplace transform is linear in the same sense. So, and the inverse Laplace transform is linear. And note that, so when we say Laplace transform f of t, let's say is equal to capital F of s, this is same as saying that inverse Laplace transform capital F of s is equal to f of t. This is the job of an inverse function. Inverse function, as you learned in pre-calculus, changes the input with output. Every input becomes output, every output becomes input. So Laplace transform f of t equals capital F of s is same as saying that inverse Laplace transform capital F of s is same as f of t. Also, Laplace transform, inverse Laplace transform is linear. So inverse Laplace transform f1 or capital F1 of s plus capital F2 of s will be same as inverse Laplace transform capital F1 of s plus inverse Laplace transform capital F2 of s, and inverse Laplace transform C times capital F of s will be same as C times inverse Laplace transform capital F of s. So this is about Laplace transform and inverse Laplace transform. And we also derived a Laplace transform of some basic functions. So we derived the table basically. So derived the following table. So here we have list of some functions f of t, and this is in the right column we have their Laplace transform. So let's say if the original function is t to power n, then the Laplace transform would be n factorial over s to power n plus 1, e to power at. Then the Laplace transform is 1 over s minus a. And in general, if I multiply like e to power at with a function, like e to power at times f of t, e to power at times f of t, this would be capital F of s minus a. And here with capital F of s being Laplace transform f of t. And the other functions that we looked at, for example, sine t besides 1 over s squared plus 1, cos t, s over s squared plus 1. In general, we can generalize this to sine, let's say, omega t or cos omega t. If it's sine omega t here, then I would have omega over s squared plus omega squared. And for cos omega t, I would have s over s squared plus omega squared. And so we also looked at the Heaviside function u of t minus a. So this one, e to power minus as divided by s. And in general, if you have, let's say, u of t minus a times f of t minus a, then it would be e to the power minus as times capital F of s. U of t minus a times f of t minus a is e to the power minus as times capital F of s. And how did we define this Heaviside function? If you remember the definition, u of t minus a is equal to 0 if t is less than a. For t less than a, the function is 0. And it's 1 if t is bigger than or equal to a. So this is how the Heaviside function is defined. And like I said, a very important property is about Laplace transform of derivatives. So Laplace transform of f prime of t is s f of s minus f of 0. And again, here, capital F of s is Laplace transform f of t. So if I have access to Laplace transform f of t, I can find Laplace transform f prime of t. That will be simply s f of s minus f of 0. And as I mentioned earlier, when you apply Laplace transform to derivative of a function, the derivative will be disappeared. So in the right-hand side, as you can see, there is no derivative. Similarly, even for the second derivative, if you apply Laplace transform, again, the derivative will be disappeared. So for example, f double prime of t will be like s squared f of s minus s f of 0 minus f prime of 0. And again, capital F of s is the Laplace transform f of t. And you can similarly, go to the higher derivatives. For example, f third derivative will be s cubed f of s minus s f of 0 minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. And so on. And we can continue this. So this is about Laplace transform of derivative of a function. We also calculated Laplace transform of antiderivative of a function. So let's say if you have integral 0 to t, let's say f of L dl. So as mentioned before by FTC part 1, this is an antiderivative for f, because as long as this small f is continuous function or piecewise continuous, then this will be differentiable and derivative of this function will be f of t. So this is an antiderivative for f. And what will be the Laplace transform of this function? It will be capital F of s over s. And again, here capital F of s is Laplace transform f of t. So this is Laplace transform of antiderivative. And then we also calculated Laplace transform of convolution of two functions. So f star g of t, which is defined as integral 0 to t, f of tau, g of t minus tau, d tau. So convolution of two functions defined by denoted by f star g of t, defined this way. What is this Laplace transform? The Laplace transform will be simply capital F of s times capital G of s. And here again, capital F and capital G are Laplace transforms of f and g. So here, capital F of s is Laplace transform f of t, and capital G of s is Laplace transform g of t. So these are some important Laplace transforms. Let's look at an example how we can apply Laplace transform to solve a differential equation. So for example, use Laplace transforms transforms to find the solution of x double prime plus x equals sine t with x of 0 equals x prime of 0 equals 0. So this is a second order ODE, linear ODE. And we saw previously that we could use other methods such as variation of parameters or undetermined coefficients to solve this ODE. Please note that this is non-homogeneous because right-hand side, the function is non-zero. But we already explained before how to solve a second order or non-homogeneous second order ODE with those methods. Now here we want to use Laplace transform. So basically you can do this problem with three different ways. You can do it with variation of parameters or with undetermined coefficients or with Laplace transforms. So here we want to use Laplace transforms. So let's apply Laplace transform to both sides. So apply Laplace transform to both sides. Then what do we get? We get Laplace transform x double prime plus Laplace transform x equals Laplace transform sine t. Remember that Laplace transform, we said that it's linear. So Laplace transform of addition of two functions will be addition of the Laplace transforms. And now Laplace transform x double prime will be s squared minus s squared capital F of s. I can call it capital X of s, the Laplace transform of small x. I can call it capital X of s minus sx of 0 minus x prime of 0. But x of 0 and x prime of 0 are both 0 according to my assumption. So this is s squared capital X of s. And here, capital X of s, I'm assuming it's Laplace transform x. So I will have s squared times capital X of s plus capital X of s equals Laplace transform sine t. Laplace transform sine t, we know it's 1 over s squared plus 1. So then I'll get a capital X of s times s squared plus 1 equals 1 over s squared plus 1. And then that gives me capital X of s as 1 over s squared plus 1, the whole squared, which is same as 1 over s squared plus 1 times 1 over s squared plus 1. Now, x of t, which is the function I'm looking for, will be inverse Laplace transform of this. See, once we apply the Laplace transform, all the derivatives will be disappeared. We'll have an algebraic equation. We can solve this algebraic equation to find capital X of s. And then we can apply inverse Laplace transform to find the original function. So x of t will be inverse Laplace transform capital X of s, which will be same as inverse Laplace transform 1 over s squared plus 1 times 1 over s squared plus 1. Now, we know inverse Laplace transform of product of two functions is the convolution of the original functions. Laplace transform of convolution of two functions is the product of Laplace transform. So that means inverse Laplace transform of the function in the right-hand side is the function in the left-hand side. So because we know that Laplace transform f star g of t is equal to capital F of s times capital G of s. So we can say that x of t will be here f star g of t, where what are f of t and g of t? F of t is inverse Laplace transform of 1 over s squared plus 1, which is sine t. And g of t will be inverse Laplace transform of, again, 1 over s squared plus 1, because here both my capital F and capital G are 1 over s squared plus 1, as you can see here. And this is also sine t. So we can say that x of t will be f star g of t. And that's integral 0 to t. If you remember, the formula was f of tau g of t minus tau d tau. And now this will be integral 0 to t sine tau sine t minus tau d tau. Now this one will be sine A sine B. We can use the formula. What was the formula for sine A sine B, if you remember? Sine A sine B was 1/2 cos A plus B minus cos A minus B. So cos A minus B minus cos A plus B. Because cos A minus B will be cos A cos B plus sine A sine B. And this will be cos A cos B minus sine A sine B. So this will be, this can be written as 1/2 integral 0 to t cos the addition of these two, A and B, which will be t. And the subtraction first, A minus B here will be 2 tau minus t minus cos the addition. Addition will be t. And then d tau. Now, what is the antiderivative of cos 2 tau minus t? So 1/2 sine 2 tau minus t divided by 2, because if I differentiate this function respect to tau, integration is over tau. So if I differentiate this respect to tau, I'll have 2 cos 2 tau minus t. So that I have to divide by 2 so that 2's will cancel out each other. And then antiderivative of cos t respect to tau is tau minus tau cos t. And it will be calculated between 0 and t. See, this is cos t, but I have to integrate respect to tau. So it's considered as a constant. For example, what is antiderivative of 5 respect to tau? It will be 5 tau. Similarly, antiderivative of cos t respect to tau will be tau cos t. Now, if I calculate this between 0 and t, I'll get 1/2 times sine. If I replace tau with t here, 2t minus t will be t. So sine t divided by 2 minus t cos t. And if I replace tau with 0, I'll get, so it will be minus, replace tau with 0, I'll have sine minus t, which is minus sine t divided by 2. And if I replace tau with 0 here, that will be 0. And then it will be 1/2 times, now sine t over 2 plus sine t over 2, that will be sine t. So sine t minus t cos t. So this will be our final answer. All right, and the last topic we looked at this course was about power series method. Power series method. So in this chapter, we considered, again, a linear ODE of the form P of x times y double prime plus Q of x times y prime plus R of x times y equals 0. Then we said that if x equals x naught is an ordinary point for this ODE, meaning that P of x naught is not equal to 0, then we can consider a solution in the power series form let's say y equals sigma an times x minus x0 to power n, and from 0 to infinity. So if P of x0, the coefficient of y double prime, if we call it P of x, if P of x0 is not 0, then we can consider a solution of this form. And then we still need to find the coefficients an. How do we find the coefficients an? And to find the coefficients or ans, find a recursive relation for an. And how do we find the recursive relation? By substituting y into the original ODE if we substitute this y into the original ODE, and then we simplify, we compare the coefficients, we can find the recursive relation for an. And so to find an, find the recursive relation for an, then find all ans in terms of a0 and a1. So we can find all the coefficients like a2, a3, a4, and every an for n bigger than or equal to 2 in terms of a0 and a1. What about a0 and a1? We are not going to find them because remember that we have a second order ODE here, and the general solution will include two arbitrary constants. Those two arbitrary constants in this case will be a0 and a1. But once we find every other an in terms of a0 and a1, we can form the general solution in terms of a0 and a1, and then form the general solution. Form the general solution. Y equals sigma an x to power n, and from 0 to infinity in terms of a0 and a1. So the general solution will include two arbitrary constants a0 and a1, and all other coefficients will be found in terms of these two arbitrary constants. Let's look at a simple example here. Find the general solution of y double prime minus y equals 0. So here, what is P of x? P of x, the coefficient of y double prime is 1. So P of 0 is not equal to 0 because P of x is the constant function 1. So P of everything is non-zero. So we can set x0 to be 0. And then y will be sigma an, x minus x0 to power n, and from 0 to infinity. But x0 is 0, so I can write it as sigma an x to power n, and from 0 to infinity. And then substitute back. Substitute back. What do we get? We need y double prime. In order to substitute back, we need y double prime. So this is y. What will be y prime? Y prime will be sigma n an x to power n minus 1, and from 1 to infinity. I can start n with 1 because 0 times anything is 0. So I can start the sigma with 1. And then y double prime, which will be derivative of y prime, will be sigma n times n minus 1, a n x to power n minus 2, and n will start from 2 to infinity. Now, what do we know? We know that y double prime minus y is equal to 0. So that means sigma n from 2 to infinity, n times n minus 1, a n x to power n minus 2, minus sigma a n x to power n, and from 0 to infinity is 0. So we also saw an important property of sigmas, and we saw that, let's say, if you have sigma a n, let's say n from m to infinity. Now, if you want to change n to n plus L, if you change n to n plus L, then the starting point will have shift L units to the left. So starting point will be n from m minus L to infinity. Similarly, if you want to change n to n minus L, the starting point will have shift L units to the right. So n will start from m plus L to infinity. So if you change n to n plus L, shift L units to the left. If you change n to n minus L, shift L units to the right. So here, in order to be able to combine these two sigmas, I need the powers to be same and also starting points to be same. But if I change n to n plus 2 here, the power becomes n, and the starting point will have shift 2 units to the left and will start from 0 to infinity. In that case, the powers and the starting point both will match together. So let's change n to n plus 2 for the first sigma. So then I'll have sigma n plus 2 times n plus 1, a n plus 2, x to power n, and from 0 to infinity, minus sigma a n x to power n, and from 0 to infinity equals 0. So I just simply replace n with n plus 2 in the first sigma, and the starting point shifted 2 units to the left. So it started from 0 to infinity. Now that the powers match, the starting points match, I can combine them and write it as sigma n from 0 to infinity, n plus 2 times n plus 1, a n plus 2 minus a n times x to power n equals 0. Now, by comparing the coefficients, the right-hand side is a constant function 0. That means left-hand side, every coefficient must be 0 as well. So by comparing the coefficients, we can say that n plus 2 times n plus 1, a n plus 2 minus a n has to be 0. So that means a n plus 2 is equal to a n divided by n plus 2 times n plus 1. And this will be valid for n bigger than or equal to 0. Because the sigma starts from 0 to infinity. So this equation will be valid for n bigger than or equal to 0, which means this equation will be valid for n bigger than or equal to 0. Now, if I replace n with 0 here, what do I get? I'll get a2 equals a0 over 2 times 1, which means a0 over 2 factorial. If I replace n with 1, I'll get a3 equals a1 over 3 times 2, which means a1 over 3 factorial. If I replace n with 2, I'll get a4 equals a0 divided by a0 divided by, if I replace n with 2, so a2 divided by, I'm replacing n with 2 here. So a4 will be a2 divided by 4 times 3. 4 times 3. But what was A2? A2 was A0 over 2 factorial. So A0 over 2 factorial divided by 4 times 3. That will be A0 over 4 times 3 times 2 factorial. And that's A0 over 4 factorial. If I replace n with 3, I'll get A5 equals A3 divided by 5 times 4. A3, I already knew that it was A1 over 3 factorial. So A1 over 3 factorial divided by 5 times 4. This will be A1 over 5 factorial. Similarly, n equals 4, then A6 will be A4 divided by 6 times 4. And that will be A0 over 4 factorial divided by 6 times 4. This is A0 over 6 factorial. So continuing this, so n equals 2k. A2k will be A0 over 2k factorial. If you look at the even indices, for A2, A0 over 2 factorial, A4, A0 over 4 factorial, A6, A0 over 6 factorial. So if you continue this way, A2k will be A0 over 2k factorial. And what about n equals 2k plus 1? A2k plus 1 will be A1 over 2k plus 1 factorial. As you can see here, if you look at the odd indices, A3 was A1 over 3 factorial. A5 was A1 over 5 factorial. And so on. A2k plus 1 will be A1 over 2k plus 1 factorial. So now we can write the general solution. So that's the general solution. General solution can be written as follows. We can say y is equal to sigma an x to power n, and from 0 to infinity. So we can write this one as a0 plus a1x plus, now a2. A2 was a0 over 2 factorial. So a0 over 2 factorial x squared. Then a3 was a1 over 3 factorial x cubed. A4 was a0 over 4 factorial x, a0 over 4 factorial, then times x to power 4, then a1 over 5 factorial x to power 5, and so on. Then we have a2k over 2k factorial x to power 2k plus a2k plus 1 over 2k plus 1 factorial x to power 2k plus 1 plus dot dot dot. So I can regroup the terms that contain a0 together. So this one, this one, this one. So this was a0 over 2 factorial. And this was a1 over 2k plus 1 factorial. So this one. And then regroup the terms that contain a1 together. So this one, this one, this one, and this one. So regroup them together. So I will have a0 times 1 plus x squared over 2 factorial, x to power 4 over 4 factorial, and so on, plus a1 times x plus x cubed over 3 factorial, x to power 5 over 5 factorial. And then the generic term here was x to power 2k, x to power 2k over 2k factorial. And the generic term here was x to power 2k plus 1 over 2k plus 1 factorial. And I can write this one as a0 y1 plus a1 y2. And here a0 and a1 And here y1 and y2 are linearly independent solutions for my ODE. A0 and A1 are two arbitrary constants. And y1, y2 are two linearly independent solutions. So we regroup them together, terms with A0 together, factored A0 out, terms A1 together, factored A1 out. And we wrote it as A0 y1 plus A1 y2. And what is y1 and y2 here? Where y1 is equal to 1 plus x squared over 2 factorial, x to power 4 over 4 factorial, x to power 2k over 2k factorial, and y2 x plus x cubed over 3 factorial, x to power 5 over 5 factorial, x to power 2k plus 1 over 2k plus 1 factorial plus dot 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 are two linearly independent solutions of our ODE, which was y double prime minus y equals 0. So we wrote the general solution as A0 y1 plus A1 y2. And this is y1, this is y2. Now in some questions, y1 and y2 can be written in terms of elementary functions such as exponential function or polynomials or trigonometric functions. But in some questions, these y1, y2 cannot be written in terms of elementary functions. In this question, y1 and y2 can be written in terms of elementary functions. What are they going to be? So check as an exercise that y1 and y2 can be written in terms of elementary functions as follows. We can write y1 as, so this is y1. We can write it as e to the x plus e to the minus x divided by 2. And similarly, y2 can be written as e to the x minus e to the minus x divided by 2. And e to the x plus e to the minus x divided by 2 was defined as cos hyperbolic x in pre-calculus, if you remember. E to the x plus e to the minus x is defined as cos hyperbolic, and this one is defined as sine hyperbolic. Cos hyperbolic x is a function that is defined as e to the x plus e to the minus x divided by 2, and sine hyperbolic x is a function that is defined as e to the x minus e to the minus x divided by 2. So how can you check that y1 and y2 can be written as e to the x plus e to the minus x over 2 and e to the x minus e to the minus x over 2? Well, you simply need to use the Taylor series for e to the x. So hint, use the Taylor series for e to the x. E to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on, which can be also written as sigma x to power n over n factorial, n from 0 to infinity. So if you use the expansion of e to the x, then you can also find the expansion of e to the minus x. Just replace x with minus x here. You will find the expansion of e to the minus x. Then if you calculate this, simplify, you will see you'll get y1. If you calculate this and simplify, you will see you get y2. Okay, guys, so this is a review. This was a review for our course Math 230. We basically covered 5 main topics, and in this course during the semester, and today we had a quick review about them. Of course, we couldn't cover everything because it was just a quick review. We wanted to mention as much as we could, like in just less than 2 hours or around 2 hours. So of course we couldn't cover many materials that we did during the semester, but I try to cover the important topics that we did during the semester. Okay, guys, and that's all. Thank you very much and hope to see you in the other courses.